So in this problem on the quiz, I asked you to find an angle theta such that sine of theta is 2.345. And then so we know to find an angle, we grab our calculator, we do inverse trig functions. And then we ask it, what is sine inverse of 2.345? And the calculator is like, oh, no, it gives you an error. Specifically, it gives you a domain error. This is because there is no angle that has a sine of 2.345. Let's see why this makes sense if we think about what the trig functions represent. So, let's be specific. Also, it throws the error code in all caps, so it's like all yelling at you, which is like just excessive. I mean, like, calm down, calculator. Especially annoying because, I mean, it throws this in all caps and it clearly has lowercase letters. So the value entered is not allowed in the function or command. So let's think about why this is. In a right triangle, we've got a right angle, and opposite the right angle is a hypotenuse. What's this vertical leg of the triangle called in relative to this angle theta? Opposite. And this one down here, adjacent. Always identify your hypotenuse first, then whatever angle you're talking about, you can use the words opposite and adjacent. If you don't have an angle labeled in your triangle, then you don't get to start talking about opposite and adjacent, because there's opposite what or adjacent what. And we have sine of theta in terms of opposite, adjacent, and hypotenuse. What is the sine of theta? Sine is opposite over hypotenuse. Now let's think about this triangle. Is theta, the angle theta, going to be bigger than 90 degrees? Can theta be bigger than 90 degrees? No, why not? We've already got a 90-degree angle. We've already used up 90 of our 180 degrees in having a right angle. So we've used up 90 degrees here. We've only got 90 degrees left to split up between the other two angles, because the sum of the angles in a triangle has to be 90 degrees. So here's a 90-degree angle. That means there's only 90 degrees to split between the other two angles. That means in a right triangle, the right angle has to be the biggest angle. Any questions? Exhibit 1, the right angle is always going to be the biggest angle. What that means is that the hypotenuse has to be the biggest side. The 90-degree angle must be the biggest angle. So the hypotenuse must be the biggest side. In a right triangle, the hypotenuse has to be the biggest side because it's opposite the biggest angle. The smallest side will be opposite the smallest angle. The middle side will be opposite the big angle. This is known as the Brady Bunch rule. I'm just kidding. It's not called that at all. This existed long before the Brady Bunch. But in the Brady Bunch, Marsha was opposite Greg. Jan was opposite that middle kid, and the youngest girl was opposite the youngest boy. I can't remember what any of their names are anymore. Cindy, Bobby. Wait, Bobby is the youngest? And then Jan, and so typical. No one remembers the middle child. Is anybody here a middle child? I'm an only child, so no one forgets me. Also, ego problems. But anyway, biggest angle has to be opposite the biggest side. Smallest angle opposite the smallest side. Peter, yes, thank you. Time for change. And the middle angle will always be opposite the middle side. So since the 90-degree angle has to be the biggest angle, the hypotenuse has to be the biggest side. Now let's look at what we're doing when we build the ratio. Sine of theta is opposite over hypotenuse. Whatever we get for opposite, it has to be smaller than hypotenuse. So we know that opposite must be smaller than hypotenuse. What that means is if we make a fraction and the numerator is definitely smaller than the denominator, that means that this fraction must be less than 1. So a fraction where the numerator is smaller than the denominator is going to be less than 1. So right away, when we look at sine of theta is equal to 2.345, we know that there is no angle it's not possible for the sine of theta to be 2.345, because that would mean that the opposite side is 2.345 times as long as the hypotenuse, and that's not possible. The hypotenuse has to be bigger. I think one of the possible answers that I had for this is undefined. Not really the best choice for this, but I think that one works. I had to put a whole variety of possible answers that you might type in, but it ain't going to be a number. It can't be a number. There is no such angle. So go back on this one and try typing undefined. I think I left that as one of the choices, or not possible, or no such angle. I should just put nope, but error, I didn't take error. I'm pretty sure I didn't put error. Because error, it just means the calculator can't do the calculation, and we want to be specific about why the calculator can't do this calculation. Yeah, I should have taken none, but NA. I should have taken NA as well. See, I can't do this until I see all your responses. But last time I did this was the first time I did this, so I started taking some of the responses there, where students were getting all mad and throwing stuff at me and cursing me. And I said, oh, that's a good one. That happened a lot. I'll put that one to the list, but I'm sure you all just added some more stuff to the list now too. What? Yeah. Uh-huh. CSC is cosecant. Okay, so we haven't talked about the reciprocal functions yet. So this was not a bug, this is a feature. I often will send you off to do problems that I haven't talked about in class. It's very sneaky of me, very mean, especially to do it over the weekend. But yeah, but reading math books is like if I assign homework and it said read section 1.1, students be like, oh, no homework. So on that problem, what we know is that sine of theta, there are reciprocal functions. Sine of theta is the reciprocal of the cosecant of theta. And cosecant theta is the reciprocal of sine theta. So this function is called cosecant. We also have a reciprocal function for cosine, which is called secant. So we could say cosine theta is the reciprocal of secant theta. Or we could say that secant theta is a reciprocal of cosine theta. So SEC is our abbreviation for secant. I can't leave the last one out. Tangent and cotangent are reciprocals of each other. So COT is cotangent. We have to remember that sine and cosecant are reciprocals. Cosine and secant are reciprocals. Tangent and cotangent are reciprocals. So some of the problems involve relationships between our trigonometric functions. Here's one set of relationships between our trigonometric functions. These are called identities because they're true for all values where the expressions are defined. All right. So the problem that you're asking about has an expression that says sine and then 90 minus theta or something minus theta. Let's talk about that. $70 minus X, okay. Let's look at a right triangle and let's label both of the angles. Let's label the angle on the bottom as theta and the angle up at the top as phi. And we've got a right triangle, so theta. Right triangle down here at the bottom. So tell me about theta and phi. What happens if I add those together? How much do I get? 90. So theta plus phi is equal to 90 degrees. What do we call it when angles add up to 90 degrees? Complementary. So these are complementary angles. Theta and phi are complementary. We've labeled the hypotenuse because every time we look at a right triangle, we have to label the hypotenuse to make sure that we can identify things like opposite and adjacent. Now we've got two angles named. So one of the sides, this vertical side, is opposite theta. But how is this vertical side related to phi? It's adjacent to phi. Now this horizontal side down on the bottom, that is adjacent to theta. But what is it relative to phi? It's opposite phi. So if I start looking at my trig ratios, if I set up the sine of theta, I take the opposite of theta and divide by the hypotenuse. Note that I wanted to be specific about which opposite. That vertical is opposite theta, the horizontal one is opposite phi. So I want to make sure I label that as opposite theta. But opposite theta is the same as adjacent to phi. And which trig function is adjacent over hypotenuse? Cosine. So the sine of theta is equal to the cosine of phi, because the side opposite theta is the side adjacent to phi, and the hypotenuse is still the hypotenuse. The sine of theta is the cosine of phi. Now, theta and phi are related. Theta plus phi is equal to 90 degrees. So that means phi is 90 minus theta. So now if I put this into the cosine, I can see that cosine of 90 minus theta is equal to the sine of just theta. The sine of an angle is equal to the cosine of the complement of that angle. I can also write theta in terms of phi. I could say that theta is 90 minus phi. So I could say that the sine of 90 minus phi is equal to the cosine of just phi on its own. The sine of an angle is equal to the cosine of the complement of that angle. That's how we would have to say that in words if we didn't have the benefit of the technology of algebra. So in the problem, we want to write the trig function in terms of its cofunction. So sine and cosine are cofunctions. We just got to figure out which of these two angles add up to 90 degrees. Which of these two angles are complementary? First of all, we want the sine and cosine. So it's not these first two, because cosecant is not the cofunction of sine. Cosine is the cofunction of sine. So it's got to be one of these three down here. Now I just got to figure out which set of angles adds up to 90 degrees. Is it 80 minus x and 10 plus x, 80 minus x and 80 plus x, 80 minus x and 10 minus x? You might have different values of 80 and 20, but it's going to work the same. Add up to figure out which pair of angles adds up to 90 degrees. So I've got 80, I got a minus x and a plus x. If I add those angles together, the x's will cancel out. And then 80 plus 10 is going to be the 90. So here down here, 80 plus 10 is also 90, but I'll have minus x will be minus 2x. That's not what we want. I want things to add up to 90. And in this second one, 80 minus x and 80 plus x, that adds up to 160. That's not what we want. So I think it's this one here. The numbers are probably different. If you had 78, then the other one was 28 or 22. 78 and 22 add up to 90. Any questions? Oh, we'll get which problem from 1.5? Take a look at the satellite problem. I like how the books try to be like current and stuff like that. So they publish, but the problem is it's like a published printed book. And so like Dish TV, it's like, well, no one does that anymore. I mean, does anybody under the age of 50 have a satellite dish? Yeah, unless you're like living at home, which is like, you know, or do you just stream stuff and then cancel your streaming service as soon as the show that you want to watch has been binged? It's all the same. So in this problem, your Dish TV antenna has a pointing error of some fraction of a second, 1/5 of a second. So the first thing that we have to deal with, oops. So this is 1.5. What was that problem number 7? So it might be 1/4, but I think they're all the double parentheses or the double quotation marks, which is a measurement in seconds. So this is 1/5 of a second, but not a second in terms of time, a second in terms of a piece of an angle. One second is 1/60th of a minute. and 1 minute is 1/60th of a degree. So one way to break degrees up is in decimals. Those are everybody's favorites, even though 10 is kind of a trash number. It's just popular because we use it a lot. 360 and 60, much better numbers because it's divisible by so much stuff. Like 10 is terrible. It's divisible by 2, it's divisible by 5. 12 is so much better. 12 is divisible by 2, 3, 4, 6. So much better. Anyway, I digress. So if we want to think of this 1 second of 1 second angle, that's 1/5 of 1 second angle. This is 1/5 of 1/60th of a minute, and that's 1/60th of a degree. So 1 degree is 60 minutes. 1 minute is 60 seconds. And so that means 1 degree is 6 times 6 is 36, and there were 2 zeros. So 1 degree is 3,600 seconds. So we're dealing with a very small part of a degree. And I forgot what was the question. So we know that the satellite is 35,000 kilometers away. I'm going to exaggerate my drawing. So I'm going to exaggerate my drawing here. This whole piece up here, this is the satellite. And the reason I drew it curved, it's not the path of the satellite. That's the satellite itself. That's how long the satellite has to be. And we want to round this to the nearest meter. Strategy number 1. I want to calculate the arc length with this radius of 35,000 kilometers and this angle of 1/5 of a second. We can calculate an arc length using a radius of 35,000 kilometers and an angle of 1/5 of a second. So that means we have to know arc length. Fun fact, you all already know the arc length formula. You just only know it for like one arc, usually. What's the formula for the circumference of a circle? Two pi r. Where r is the radius of the circle and 2 pi is the angle of the central angle of the arc. But how much of a circle is 2 pi? 2 pi is the whole circle. So we're just taking the angle in radians times the radius. So if I want to know the circumference of half of a circle, what's my angle for half of a circle? 180 degrees, 180 degrees, which is how many radians? Pi radians. We just took half of what we had. What we need now is just 1/5 a degree, 1/5 of a second converted into radians. And that's one way we can approach this problem. So for arc length, is just theta times r, where theta has to be in radians. Any questions? So this is our plan. This is not an answer yet. This is just our plan. We're just going to multiply our angle by our radius. The problem is that the units are all messed up. So annoying. So here we're going to get the wrong units, because our units here are kilometers and our units here are seconds. And I need those to be radians. I need these to be meters. How do I turn kilometers into meters? What's the relationship between kilometers and meters? 1,000 meters is 1 kilometer. So am I making more meters or less meters? You're going to think about this in two different ways. A mechanical way, and then thinking about what we know is supposed to happen. I've got 35,000 kilometers. If I'm going to convert that into meters, am I going to have more of them or less of them? More, because there's 1,000 meters in every 1 meter. So I need to be making this number bigger. So am I going to multiply by 1,000 or divide by 1,000? Multiply, because I'm going to be making stuff bigger. So multiplying by 1,000, that'll make things bigger. So we know that we're going to be multiplying by 1,000. Let's think about it mechanically, just knowing what we want to happen. I want to get rid of this measurement called kilometers, and I want to replace it with a measurement called meters. So I want to divide by kilometers and replace that with meters. And so I'm going to write 1 kilometer is 1 meter. I know I'm going to put 1 kilometer on the bottom because I want kilometers to go away and leave behind meters. So if I have kilometers up here and I divide by kilometers, kilometers cancels. Mechanically, we know what's supposed to happen. More meters, or sorry, just thinking about the measurements, we know what's supposed to happen. This number has to get bigger. There are more meters than there are kilometers. So that's the first thing that we're going to do. And mechanically, we put the kilometers on the bottom because I want those to cancel out. Now I've got meters. That's good. Over here, I've got seconds. Seconds ain't no good. I need this to be in radians. So let's go to, we know that there are 360 degrees is equal to 2 pi radians. Is that useful to us yet? You can tell by the way I asked the question, the answer is no. So Michael, is that useful to us yet? It's like, oh, no, just by the tone of your voice, you can tell that the answer is no, right? So now you're like, oh, why didn't you just say, that's not useful to us yet? Because it sounded like a question when I said it, so I made it a question. That's not useful to us yet because we're looking at seconds. I can't cancel out degrees and seconds. That's not how it works. I need to convert my seconds into degrees. So if I've got 1/5 of a second, do I have a lot of degrees or very little degrees? Very little degrees. Mechanically, I want to cancel out seconds and replace them with degrees. And we know that 1 degree is 3,600 seconds. This makes sense because we're not going to have very many degrees because degrees are bigger. It makes sense that we're going to keep dividing. Also, mechanically, we cancel out seconds by putting the seconds on the bottom, and we're left with degrees on top. But this is not what we want. We want radians. I know 360 degrees is 2 pi radians. Where's the 360 going to go? The 360 goes with degrees. And so then I could put 2 pi radians on the top. Now I know what sequence of buttons I have to push. I'm going to start with the 1/5. 1/5 is a 0.2. So I'm going to do 1/5 times 35,000. The numbers on top, I'm going to multiply. This is going to be in kilometers. So I need to multiply by 1,000 to get it into meters. Then I'll need to divide by the 3,600. That's going to give us degrees. The 2 pi is on top, so I'm going to multiply by the 2 pi. And the 360 is on the bottom, so I'm going to divide by 360. questions? What's that? So 1 degree is 3,600 seconds, because 1 degree is 60 minutes, and 1 minute has 60 seconds. So if you do the 60 times the 60, 1 degree is 3,600 seconds. I need to cancel out seconds so I can get to degrees, so I can use 2 pi radians is 360 degrees. So we're doing a lot of unit conversions in this case, and we just got to use the ones that we knew. So I wanted to go from from seconds all the way to radians. I didn't know the relationship between seconds and radians, so I just used the relationship between degrees and radians and degrees in seconds. So for example, if I want to know how many inches are in a mile, I don't know the ratio of inches to mile. I don't know how many inches there are in 1 mile, but I know how many feet there are in a mile, and I know how many inches there are in a foot. So I can go from 1 mile to feet, and then from that number of feet to inches. How many feet are in a mile? Obviously, it's 5,280. That makes perfect sense. I like how England makes fun of us. England invented this shit. I don't want to hear anybody in the UK be like, "Oh, Americans measuring things in washing machines." Blah, 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 blah. Motherfucker, you invented this. So I don't know how many feet there. I don't know how many inches there are in a mile, but I know how many feet there are in a mile, and I know how many inches there are in a foot. How many inches are there in a foot? So I'm gonna have 12 inches and 1 foot. 1 foot has to go down here because I want the foots to cancel, and I put 12 inches on top. So now mile cancels out mile. Foot cancels out foot. And it makes sense. So it makes sense mechanically by canceling stuff out. And it makes sense because 1 mile will be a lot of feet and even more inches. So I'll just take my 1, I'll multiply by the stuff on top and multiply by the stuff on top. Makes sense. We're going to have a big number, 63,360 inches. If I had to translate this into meters, the only one that I can remember is 1 inch is 2.54 centimeters. So I had to go from miles all the way down to inches, inches over to centimeters, centimeters back to meters or whatever I'd said before. Any questions? Is everybody okay? Yeah. Which problem? Is that the one with the 4-foot windshield? It's like 3 foot vertical. I mean, yeah. So I was in 1.3. I remember that one. All right. All right. Automotive design. This one kind of bothers me because the distance from the top of the windshield to the horizontal plane of the dashboard is 4 feet. Now, I wouldn't care so much if they're like, oh, this is an Amazon delivery truck or something, but this is like a car. Like, oh, dude, 4 feet, come on, man. You can't just like put random numbers in places. And then, I mean, it's perfectly acceptable to say, here's a right triangle where this vertical leg is 4 and the tangent of the angle is a square root of 3. And no one would question it. But what bugs me is that they say, oh, let's make it applicable to their lives. It's like, no, no one cares. We just look at this and say, that's way too much. It's not 4 feet. You know what I mean? But then again, how many of you didn't notice that this was an extremely tall greenhouse on the car? Did anybody notice that at all? Am I the only one? I mean, that's like a lot of window. I don't know, maybe I'm the only one, but it's things like this, and I think I've talked about this before. This is why we measure shit in washing machines. How tall is 4 feet? I'm standing here. How tall is 4 feet? it's about you know, about half a washing machine. No, a washing machine is like 3 feet tall, so it's like 1 1/3 washing machine in height. 2/3 of Professor Leach in height, and 6 feet tall. Anyway. Bugs me. How long is this? How wide is this room? Side to side. How wide is this room? How many cars could you fit? Park. If this is like a section of street, how many cars could you park here? 4? Have you seen modern cars? How long is a car? F-150. 4-door, short bed. I'll keep it simple, something that's more consistent. Minivan. How long is a minivan? 12 feet? This is America. We've only got one size of minivan. Odyssey, Sienna, same length. See, measuring things in meters, in feet, for the most part, doesn't help, right? From just reporting standpoint. Anyway. All right, in this problem, 1.3. Our gigantic windshield. We have an angle of theta. We call this dashboard. We call this just Y because we don't have a name for it. And we call this windshield. Here's what we're given. On my particular problem, Y is given at 4 feet. And we also know that the tangent of theta is equal to the square root of 3. There are a few ways that we can go about this problem. Number one, we could recognize that if the tangent of theta is equal to the square root of 3, that tells us that angle theta is equal to 60 degrees, because we just recognized that. It might be that we have enough experience that this tells us theta is 60 degrees. We know stuff. It might just be that we recognize that this angle, tangent of theta, is the square root of 3. When I say, like, what's 7 times 8? 56, right? Do you do that by building 7 rows of 8 things and counting them up, you just recognize, right? By the end of the class, actually by the end of next week, you're going to recognize things like the square root of 3. You're going to say, oh, this is a 30-60 right triangle. This is a 30-60 right triangle. And tangent of theta is the square root of 3. You think I'm crazy, but it's totally true. Eventually, you just start recognizing stuff. Let's suppose that we didn't recognize that. Let's suppose we didn't know that at all. We'll grab our calculator, make sure we're in degree mode, and find the tangent inverse of the square root of 3. We close the square root, close the tangent inverse, and we find out that it's 60. So we don't have to recognize, we have calculators. I can't even remember what the question was. Was the question, how big is the dashboard, or is the question, how big is the windshield? How big is the windshield, I think? How long is the windshield? So we want to know the hypotenuse. Here's an angle theta. Here's the hypotenuse is 4. Oh, sorry, the side opposite theta is 4. We want to know the hypotenuse. What trig function could we use? If I have an angle and I have opposites, I want to use sine because I know the opposite. So if we want the windshield, which is a hypotenuse. We have angle and the opposite. So that tells us to use sine. So I'm going to set up sine of 60 degrees is opposite over hypotenuse. We did want to find out that angle, but we were able to do that with our calculating machine. Or we just recognize that this is one of the commonly used versions. Now, if we want to solve for the hypotenuse, if 3 is 6 divided by 2, then 2 is 6 divided by 3. So I know the hypotenuse and the sine of 60 switch places. So the hypotenuse is going to be 4 divided by the sine of 60. And we'll just take that to our calculating machine. Glare. 4.61. No. Feet, because it's a gigantic windshield. And I can't remember what it was, what you were asked to round to. Probably 4.6 feet. Question? Oh, yeah. Any questions? Let's actually take a break. That was a lot of problems. And it was wide-ranging problems. Random sampling of problems. Let's take a break, come back, and see if there are any more problems that we need to talk about.